Welcome students, welcome to this series of lectures on matrices and determinants. Matrices is one of the concepts in mathematics which is highly useful in many places. Well, let us look at an example. Suppose there are two companies A and B, and each company produces say 3 items. Suppose three items, let us give it a name 1, 2 and 3. Suppose the company A produces 70, 80 and 90 kgs of items 1, 2 and 3 respectively. Similarly, the company, so in fact let us suppose that the company B produces 90, 50 and 100 kgs of items 1, 2 and 3 respectively, right. We have the following data. What we have is that we have two companies A and B, and not only that you have, and each company, both of them produces item 1, 2 and 3. So, item 1 is produced 70 kilo by company A and 90 kilos by company B, 80 kilo of item 2 is produced by company A and 50 kilo of item 2 is produced by company B. Similarly, 90 of item 3 is produced by 90 kg of item 3 is produced by company A and 100 kilo of item 3 is produced by company B. Let us write it in some form. Let us put it in the form of a table. I have A, company A and company B, and on the other hand I have item 1, item 2 and item 3. So, A produces 70, 80 and 90, and similarly B produces 90, 50 and 100. So, this is one of the typical examples for what is known as the concept of a matrix. So, now let us write down what a matrix is. Let us put it formally in the form of a definition. A matrix is a rectangular array So, the elements of the array are called as the entries of the corresponding or the underlying matrix. Entries of the underlying matrix. So, how do we in general denote a rectangular array? This is the way you denote, right. So, A11, A12, A13 up to A1n, A21, A22, A23 up to A2n. Proceeding this way, you will have AM1, AM2, AM3 up to AMN. So, there are totally mn elements or entries in this matrix. So, given a matrix and when you write it in the form of a rectangular array, so the total number of entries that you have, so that is the totality of the whole array. So well, let us notice that there are m rows and n columns in a matrix. Well, this m and n depends on the chosen problem. And finally, the order of a matrix with m rows and n columns is m cross n, right. This m cross n denotes the order of the matrix. Now, let us do some examples. Let us begin with the first example that we started with. In the first example, we had an array. So, the matrix that we had is A, which is 70, 80, 90, 90, 50 and 100. This is the matrix that we had initially. And if you look at this matrix, so A has got two rows and 3 columns. Therefore, the order of the matrix A is, the order of the matrix A is 2 by 3, right. And you can also notice that it has got 2 into 3, that is 6 elements. Let us do another example. A, which is given by 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is the matrix. So, A has got 3 rows and 3 columns. Therefore, order of A is 3 by 3. Now, let us do a simple problem to calculate the entries of a matrix. Suppose that A is a real matrix. So, what does that mean by a real matrix? By a real matrix, we mean a matrix whose entries are just real numbers. real matrix whose order is three by 2. Find the entries if the entries are given by the formula Aij equal to modulus of I minus j whole upon 2. Let us try to solve this. So, given a matrix A, an n by n matrix A, the ijth entry will be denoted as Aij. Given A is a 3 by 2 matrix, therefore, A has 3 rows and 2 columns. So, the ijth entry is given by modulus of I minus j whole upon 2. So, therefore, the matrix A is given as A11, A12, A13, A21, A22 and A23. Let us apply the formula and get the entries. A11 which is modulus of 1 minus 1 upon 2, 1 minus 1 is 0. So, the first entry is 0. Second one A12, it is given by 1 minus 2, modulus of that is 1 whole upon 2. So, you have half. A13, so 1 minus 3 it is minus 2 and modulus of that is 2, 2 upon 2 it is 1. Second one 2 minus 1, it is going to give you 2 minus 1 is 1. So, 1 upon 2 it is again going to be half. 2 minus 2 0, again 2 minus 3 it is minus 1 and so you will have modulus of that is 1. So, 1 by 2. Thus, we have found the entries. So, now let us look at various different kinds of matrices. The first one is what is known as a row matrix. Row matrix. What is a row matrix? A matrix with just one row is called a row matrix. A row matrix will have the order 1 by n, right, where n is the number of entries in that row. So, let us look at an example. First one, just look at this one 1, 2, 3. So, this is an example for a row matrix, right, and its order is 1 by 3. Second one, let us look at one more 1 by 2, root 2, 3. So, this is again a row matrix and its order is again 1 by 3. So, in this case n is just 3. A column matrix. So, what is a column matrix? It is just the similar to the row matrix, just the matrix with just one column. A matrix with just one column is called a column matrix. So, the order of a column matrix will be n by 1, right, where n denotes the number of elements in that column. So, let us do some examples. First one, you have root 2, root 3 and root 5. So, this is an example, a typical example for a column matrix, and its order is 3 by 1. Let us look at one more example, 0, 0. This is again a column matrix, and its order is 2 by 1. Third one is what is known as a square matrix. A square matrix is a matrix in which the number of rows is equal to the number of columns. Whenever you find a matrix in which the number of rows is equal to the number of columns, then you say that such a matrix is a square matrix. Let us do some examples. Let us look at the first example that we had, 70, 80, 90, 90, 50, 100. So, what does it mean by a square? So, square matrix, number of rows is equal to the number of columns, which means the, if you say that it has got n rows, which means it should also have n columns, that means the order should be n by n, right, and we know that its order, the order of this matrix is 2 by 3. Therefore, this is not a square matrix. Let us do one more example. Well, let us write down this way, half, 1 by 4, 1 by 8, 1 by 3, 1 by 9, 1 by 27, 1 by 4, 1 by 16 and 1 by 64. So, number of rows is equal to 3, and similarly number of columns is also same as 3. Therefore, this is a square matrix. third one. Let us look at this one 1, 2, 3, 4. Here again in this case number of rows is equal to number of columns equal to 2. Therefore, this is a square matrix. So, let us make a small remark. First one, a row matrix of order 1 by n is a square matrix if and only if n equal to 1, right. If you have a row matrix of order 1 by n, right. So, when can it become a square matrix? This is possible only if n is 1. So, if n is 1, then it is a square matrix. You know that it is a row matrix of order 1 by n, and if you want that to be a square matrix, which means the number of rows should be same as number of columns, and you know that it has got just one row, therefore, it should have only one column, and you know that it has got n columns, therefore, the only possibility is that n should be 1. Similarly, second one, a column matrix of order n by 1 is a square matrix if and only if n equal to 1, right. Let us look at one more variety, one more type of a matrix, diagonal matrix. A square matrix is called a diagonal matrix if all the entries except the diagonal entries except the diagonal entries are 0. So, if you have a square matrix A11, A12, A13, A1n, A21, A22, A23, A2n, and it goes up to AN1, AN2, AN3, ANN, right. The entries, these entries, so the AII entries are called the diagonal entries. These are called as the diagonal entries, right, or the entries in the ith position. Entries in the ith position are called the diagonal entries. Let us look at an example. So, the diagonal entries are 0 and 0, of course, the other entries are also 0. So, this is an example for a diagonal matrix. Let us look at one more example. Two, 0, 0, 3. This is again an example for a diagonal matrix. Let us look at one more example. If you look at this one, the diagonal entries are 0, while the other entries, right, the entries in 1 2th position and the entry in the A to 1th position not 0, and therefore, so this is not an example. This is not a square matrix, sorry, this is not a diagonal matrix. Let us do one more example. So, all the entries are 0, you have the diagonal entries, these 3 things. But if you look at this entry, this is a non-zero entry which is not a diagonal entry, right. So, 1 is a non-zero entry in the 2th position. Therefore, this is not a diagonal matrix. Let us look at one more variety of matrix of what is known as a scalar matrix. A diagonal matrix is called a scalar matrix if all the diagonal entries are given by multiplication by a unique scalar or obtained by multiplying a unique scalar to 1, right. If all the diagonal entries are obtained by multiplying a unique scalar to 1. So, let us look at an example. Two, 0, 0, 2. So, this is an example for a scalar matrix. Second one, 2, 0, 0, 2, 0, 0. So, this is not even a square matrix and hence not even a square matrix. And hence cannot be a scalar matrix. Well, let us look at one more thing. There is something called what is known as an identity matrix. So, what is an identity matrix? An identity matrix of order n is given, it is usually denoted as I, right. So, you have 1, 0 at other places, you have 1 in the 2 tooth position and then 0 at other places. So, that means what? Aij, the ijth entry is going to be, I can write it as 0 if I not equal to j, and is going to be 1 if I equal to j. This matrix is what is known as the identity matrix. Let us try to write down the 2 by 2 identity matrix. Let me write it as I 2 by 2, it is going to be given as 1 0 0 1. Let us write down the 3 by 3 identity matrix, it is given as 1 0 0 0 1 0 and 0 0 1. This is the matrix that we have. Next one is what is known as an upper triangular matrix, variety or a type. A square matrix in which all the entries that are below the diagonal or 0, which all the entries that are below the diagonal or 0 is called an upper triangular matrix. Let us look at an example. First example, 1 2 3 0 4 5 0 0 6. So, let us first draw the line, right. So, you have this 1 4 and 6, these corresponds to the diagonal entries and the entries below that, right. You have all the entries below that or 0, therefore, this is an upper triangular matrix. Let us look at one more example. Again, so this is these two correspond to the diagonal entries, and that below this, so this is the identity matrix. So this is a upper triangular matrix. Let us look at one more example. In fact, this example is a generalization of the previous one, the identity matrix. Every scalar matrix is an upper triangular matrix. Right. So, the next one, strictly upper triangular matrix. A triangular matrix or I will write it as an upper triangular matrix is called strictly upper triangular if even the diagonal entries are zero. So, let us look at some simple examples. Zero, 1, 0, 0. So, these are the diagonal entries. The diagonal, both the diagonal entries are 0 and the one even below that is 0. So, this is an example for a strictly upper triangular matrix. This is an example for a strictly upper triangular matrix. So, let us look at the second example. 0, 2, 3, 0, 4, 5, 0, 0, 0. So, let us first mark the diagonal entries. Second example. So, you have the diagonal entries here. Fine. So, all the entries below the diagonal they are 0. So, therefore, this is an upper triangular matrix. First thing, and now let us verify whether this is a strictly upper triangular or not. So, the second diagonal entry, which is 4, it is a non-zero number, right. 4 is in the 2-tooth position, and hence this matrix is not strictly upper triangular. So, having said about the types of matrices, now let us try to do something on operations, some kind of operations on matrices. First one is what is known as addition of matrices. Two matrices can be added if they are of same order, right. Two matrices of same order, only then you can add them. If you have it as of same order, then you can add it, and the ijth entry of the resulting matrix is obtained by adding the ijth entry of the given two matrices. So, let us do an example. In fact, let us start with a simple example. Let us choose A as 1, 2, 3, 4. Let A equal to this and B as 5, 6, 7 and 8. Let us try to calculate A plus B. We want to add these two matrices. So, let us calculate A plus B, which is given by, so the first entry or the 1/1th entry is given by adding the 1/1th entries of the corresponding given matrices A and B. So, the 1/1th entry of A is 1 and the 1/1th entry of B is 5, therefore, 1 plus 5 it is 6. Similarly, the 1/2th entry of A is 2 and the 1/2th entry of B is 6, therefore, 2 plus 6 it is 8. The 2/1th entry of A is 3 and 2/1th entry of B is 7, therefore, 3 plus 7 it is going to give me 10. 2/2th entry of A is 4 and 2/2th entry of B is 8, 8 plus 4 it is going to give me 12. So, let us do second example. Let us do it for a 3 by 3 matrix. Let A equal to this 1, 2, 3, 4, 5, 6, 7, 8, 9, B equal to 9, 8, 7, 6, 5, 4, 3, 2. Let us try to calculate A plus B. Notice that both A and B are square matrices. In fact, both are of order 3 by 3 and therefore, one can calculate A plus B. So, let us calculate entry wise. So, 1 plus 9 10, 2 plus 8 10, 3 plus 7 10. In fact, you can notice that all the entries are going to be just 10. Now, let us do some properties of addition. Before we proceed further, let us discuss a remark saying that the above said details about real matrices holds without any change to complex matrices. That means what? Just like what you do for real matrices, same thing can be done even for complex matrices. You can add two complex matrices. So, same thing whatever we did for real also can be done for complex matrices. So, what is a complex matrix? A complex matrix is a matrix in which all the entries are complex numbers. Example, look at this matrix A, which is given by I, 2i, 3i, 1 plus 2i, 2 plus 3i, 3 plus 4i, root 2 plus root 3i, root 3 plus root 5i, root 5 plus root 7i. What we have are complex entries in this matrix. So, this is one of the examples for a complex matrix, and just like how you add real matrices, one can also add complex matrices. So, just like you will have to add entry wise, same thing. Now, before we proceed further with the properties of matrices, let us write down a note saying that two matrices A and B of same order are said to be equal if each entry of A equals the corresponding entry in B. So, for example, if I write A as the matrix with entries A I j and the matrix B as B I j, then A equal to B if A I j equal to B I j for all I and j, right. So, this I and j varies from 1 to n and 1 to m if you assume that A I j are of order n by m, right. With this note, let us proceed to prove some properties of matrices. For any two matrices, in fact square matrices, A and B of same order A plus B equal to B plus A. So, how to show that A plus B equal to B plus A? We will have to use the above note, that is just look at the ijth entry of A plus B and similarly the ijth entry of B plus A, one should show that these two match. Now, let us go with the proof of this. Let A equal to A I j and B equal to B I j, where 1 less than or equal to I comma j less than or equal to n. That is, we are assuming that A and B are of order n by n. Now, what we wanted is A plus B, that means we are trying to add the matrix with entries Aij and Bij respectively. If you look at this one, this is going to be same as by the definition of matrix addition, this coincides with Aij plus Bij, but what we know is that complex addition and real addition, whatever it be, they are commutative, right. For scalar, for complex scalars or real scalars, we know that addition is commutative. Let us use this fact, and therefore, Aij plus Bij, this is same as Bij plus Aij, which is same as again by the definition of addition of matrices, this is same as Bij plus Aij, that is the matrix with entries Bij plus the matrix with entries Aij, but matrix with entries Bij is the matrix capital B and the matrix with entries Aij are just A. Thus, A plus B equal to B plus C. In fact, the above said property is what is known as commutative property. So, this property is called as the commutative property. Let us prove next property. For any three matrices A, B and C of same order, A plus B plus C is equal to A plus B plus C. Let us go with the proof. The proof of this is more or less same as the one that we gave for the commutative property. So, we will assume that A equal to matrix with entries Aij, B equal to matrix with entries Bij and C is the matrix with entries Cij, right, wherein 1 less than or equal to I comma j less than or equal to n. Because all three matrices are of same order, this is possible. That means, we are assuming that A, B and C are any three matrices of order n by n. Now, what we wanted is A plus B plus C, which is equal to, we are adding matrix A, that is with entries small aij plus a matrix Bij plus a matrix with entries Cij equal to, let us do what is within the parenthesis Aij plus, if you look at within the parenthesis by the definition of addition of matrices, this is same as Bij plus Cij, which is equal to, what we are doing is we have two matrices, one with entries Aij and the other one with entries Bij plus Cij. And again, now let us try to use the definition of the addition of matrices. So, what we will end up with is a matrix with entries Aij plus Bij plus Cij. Whether they are real matrix or complex matrix, we know that addition is associative and therefore, this is same as Aij plus Bij, Aij plus Bij plus Cij. Now, let us again use the definition of the addition of matrices and then split this. This is Aij plus Bij plus a matrix with entries as Cij. But again, if you use the definition of addition of matrices, then this is same as matrix with entries Aij plus matrix with entries Bij plus the remaining which is matrix with entries Cij. If you expand or if you write on what these are, the first one is the matrix with entries Aij is the matrix A, second one is the matrix B plus matrix C. Thus, A plus B plus C is equal to the matrix A plus B plus C. So, this property is called as the associative property. So, with this let me stop for today's lecture. Thank you.